morning. Today we start on Chapter 6 on bioelectricity. So you hopefully have started reading it, continue reading it, especially sections 13 and 14 for Wednesday. You have homework due this Friday in Chapter 5. I'm going to say a little more about a couple of the problems, and then I'll open it up if anybody has any questions. And there's also then another homework assignment, Chapter 6, a week from Friday. So, on homework number 5, I wanted to talk about the last two problems, especially problem 15. 5:15 from the homework. Problem 5:15 is one very similar to the countercurrent heat exchange problem we solved, except it's going to be you're going to be deriving the differential equation. So it's kind of a simplified version of that. You're going to assume you have some cylinder, and it has a certain concentration of some substance in it as a function of z, where z is the direction along the axis. So you're trying to find c of z. And this concentration is in some fluid, and the fluid is flowing down this with speed v. And we're going to assume the outside is kept at zero concentration. So the concentration outside here is zero. And there's two ways you can transfer material. So our assumptions are when you're moving material in the z direction down the pipe, it's going by convection. Very similar like what we had in the countercurrent heat, where heat was moved by convection. But you can have also molecules move across the wall of the cylinder, and that happens in proportion to the concentration difference between the inside and outside. So it's like a diffusion process across the wall. It's just like that coupling term of coupling artery and vein was in the between the two, temperature difference. Now the nice thing about this is there's only one concentration you need, C of Z, as opposed to 2 in the artery and the vein for the countercurrent. So it's a somewhat easier problem. So what you need to do is you need to derive a differential equation, basically try to find a differential equation for dc dz, and then solve it as best you can and answer what the problem has. So you're going to be wanting to set it up in the same way we did with countercurrent heat exchange. You're going to set up a current density J. So I'll just kind of get you started. And that for convection is going to be V times the concentration. And then you're going to look at J coming into a little region, J going out, and the J crossing the membrane, which is going to be proportional to the concentration difference, and work out the differential equation. So that one's a little bit more difficult because you're not just solving something I give you, but you're actually deriving the physics behind it. So that my guess is it's the most challenging problem on the homework assignment. Then problem 16, the very last one on the assignment, isn't so difficult. It's talking about the artificial kidney like we did in class, and we derived the time constant that tells you how fast you equilibrate to the same concentration in the blood as the dialysis fluid, and you have to evaluate that time constant. So that one's pretty straightforward. So that is a little bit about homework 5. Did anybody have any questions about anything in homework 5 if you've gotten started yet? All right. Well, I would encourage you to start. So Wednesday you can bring questions to class, because I found when grading the homework that you guys sometimes you really need to take advantage of the chance to ask questions in class, so we can keep moving forward on those. Okay, so let us now go to bioelectricity. All right, so I'll erase this. And let's take my view of the cell. And we talked a little bit about this when we were talking the Boltzmann factor. But here's a cell. And on the inside of the cell, salt water. But the salt that's inside is mainly potassium. Or if it's a potassium, then an anion, usually chlorine. And on the outside, it's mostly sodium, or sodium chloride. So you have different ions inside and outside, and that we'll talk a little bit about how the cell maintains those different ions. And then this thing here is the membrane, where most of the really interesting biology takes place in the membrane. So salt water inside, salt water outside, membrane in between. And we need to talk a little bit more about what the membrane's like. So is anybody from your biology class, what's a membrane usually made out of? Lipids. In particular, it's a bilipid layer. So lipids are these long molecules with a polar head and a non-polar side chain. And they usually form in a bilayer so that the non-polar ones are attached to each other, and these polar head groups are attached with the water outside. So this would be the inside of the cell here, and this would be the outside, and you have this bilipid layer. But inside the layer, sometimes you have proteins. So proteins in our kind of cartoon here look like little potatoes sitting in the bilipid layer. So these are the lipids. And these are some of the proteins in there. And the whole thing is roughly 6 nanometers in thickness. The exact thickness depends on how you define it and whether there's sort of other pieces of protein attached to it. But 6 nanometers is on the order of how thick the membrane is. Now, what I want to do is talk about what sort of proteins you have inside the membrane. And there's 2 types. Here, one is an ion channel. Now, an ion channel kind of looks like this. Let's suppose this is the bilipid layer. Sometimes I'll draw it just as like parallel lines, but that really means a bunch of lipids like this. And then you have a channel, which is a protein, and it's a protein with a hole in the middle so that ions can go through. And there's 2 properties of these ion channels that's pretty interesting. First of all, sometimes they're gated. So I draw this like a door on a hinge. This door can swing shut and close the channel, or it can swing open and open the channel. So you have these ion channels are gated. They can open and close. Their conductance varies depending on the opening of the state. And they're also selective. Selective means that you might have a channel that can pass potassium, but it can't pass sodium, or vice versa. That's kind of an amazing statement to say that you can have a selective channel, because sodium and potassium, they're right next, or one above each other in the periodic table. They're both singly charged ions. They're almost identical, except a slight difference in size. So how do you design an ion channel that can let one through and not the other? It's kind of amazing. In particular, you might say, okay, well, I could let the small one through, but block the big one because the hole is only so wide. Well, that might explain one type of ion channel, but how do you let the big one through and the small one not? I mean, it's a really interesting question, how do you get selectivity? So ion channels are gated and they're selective, and we're going to be talking about those types of properties. The other type of ion channel or protein is the pump. The pump is a pump that pumps sodium out and potassium in. What maintains this ion concentration. And the most famous pump is what's called the sodium potassium ATPase. Okay. Sodium, potassium, that's what it's pumping. Any molecule that ends with A's is usually some enzyme, some protein molecule that catalyzes something. ATP is where you get your biological energy. So this is a protein that uses biological energy to pump sodium and potassium across the cell membrane, pumping sodium out and potassium in. And it turns out that a large fraction of your metabolic energy, your resting metabolic energy, is used by your cells to create these ion concentration gradients. So it's a big deal. And it underlies a lot of how nerve and muscle works. and that's going to mean it underlies how we move, how we think, how we send signals, how we perceive the surroundings. So we're going to be talking a lot about these. However, the pump tends to be rather slow, so that when we're trying to make a model, one of the goals of Chapter 6 is to make a model of how action potentials fire in the nerve axon. And from the point of view of a few milliseconds action potential, the pump's really slow, so you essentially can treat these concentrations as constant. But if you look over time, these concentrations would run down if it wasn't for the pump. So the pump is sort of a source of energy for the whole process. All right. Now, what I want to do is I want to look at what's happening across the membrane and try to derive a relationship between these ion concentrations and the voltage across the membrane. And we already did this once with Boltzmann's equation, Boltzmann's factor. But we're going to do it now looking at it as a competition between diffusion and convection and electrical forces. And we're going to see that you get the same result, but kind of a different physical picture. So, let us try that. Any questions on this sort of tutorial on membrane biophysics, bioelectricity? Okay. So, if we want to look at, let's look at potassium, because a resting cell membrane, most of the sodium channels are all shut, and the potassium channels are at least partly open. So that means that the resting membrane is pretty much only permeable to potassium. These channels don't let the chlorine ions go out, and they don't let any of the big proteins inside the cell out. So it's really sodium and potassium are the main two players. In muscle, calcium is a player, but not so much in nerves. Okay, so suppose we want to look at how what happens across the membrane. So we're going to look at, say, X is going to be the direction across the membrane, and we want to look at how the potassium moves in an ion channel going across the membrane. First of all, there's diffusion. So if I want to set up an equation for sort of a current density or a molecular density, let's call it a molecular density. What is that for diffusion? Does anybody remember what the J, the molecules per unit area per unit time was when you have diffusion? How do you relate that to the concentration gradient? Goes back, it's Fick's first law, if that maybe helps trigger memory. All right. Peclet, it's going to be related to the Peclet number, but it's actually not the Peclet number. That's going to be really telling you how important the two terms are. But this is more how do you drive molecules with diffusion? What is it? What's the driving force? What's causing it? Well, it's a concentration gradient. So what you have is you're going to have a concentration gradient with a diffusion constant, and then you're going to have the concentration as a function of X. So inside the membrane, inside the channel, you're going to have a gradient of the concentration. That can drive potassium, and it can usually drive potassium out because there's a lot of potassium inside, not much on the outside. So it's just would flow out through its concentration gradient. How about convection? What do you have with convection? How do you determine the number of molecules per unit area per unit time when you have convection? It's really the other half of the Peclet number. Anybody remember? Well, we had the speed times the concentration. Now, why is there a speed? You don't really have water flowing like water in a pipe, but there's going to be electrical forces that are going to cause the fluid, the molecules to move in response to the electrical force. So if you put an electric field on, you're going to get the charged particles, because these are charged ions, to begin to move, and the frictional force will oppose the motion, so it will reach a steady state very quickly, and you'll have a motion that really is the speed times the concentration. That's what we found before for convection, is the speed. So in our case, it's going to be U, and I'll tell you what U is here in a second, times the concentration. U is going to be related to a speed, but it's actually the speed per electric field. So we're going to need the electric field, which is dV dx. Okay, so let's see what this is. This is the mobility. And its units are meters per second divided by volts per meter. That is, mobility tells you how fast the ions move given an electric field of so many volts per meter. So it's really the speed. This times this voltage gradient is going to be the speed times the concentration is the number per unit area per unit time. This is the voltage. Now we're bringing in electrical concepts. Voltage is a measure of the electrical potential energy of the particles. There's going to be a voltage drop across the membrane. So this is the voltage drop, which means it's really the electric field. dV dx is the electric field. And so if that's zero, there's no motion. All you have is diffusion. There's no convection. There's the concentration. So this is really those two terms that go into the PHY number. It's the diffusion and really an electric field or resulting in convection term. And those are in equilibrium. So in the end, there you have zero motion. We're going to assume that if you didn't have that, then you wouldn't be in steady state, and there'd be basically charging up the membrane. So we're assuming the membrane charge is constant. So this might have some potassium diffusing out, but the same amount's going to be driven in by electrical forces, so you don't have a net potassium crossing the membrane. Now, there's a relationship between D and basically the mobility. And this was derived by Albert Einstein. And it's D is equal to U, the mobility, kT, Boltzmann's constant times temperature, over the charge. So that's just a fact that we're going to bring in and use. And we're going to plug that into here. So we'll get minus U kT over Q dk dx minus U k dV dx equals 0. And lo and behold, the mobility U just cancels out in equilibrium because these equals 0. So that cancels out. And we can solve this then for dV dx. So we'll bring the dV dx to the other side, get rid of that minus sign. The u's cancel out. We'll divide through by the concentration gradient. So we get dV dx equals, well, we still have minus kT over Q. You divide it by the 1 over K, and dk dx. And this then is a relationship between a voltage gradient and a concentration gradient. So we're making progress. Now, here you have 1 over K dk dy. That's kind of like 1 over y dy dx. Does anybody know how you can write that using the properties of calculus? Does that ring a bell? Well, think about the logarithm. What's the derivative of the logarithm?
1 over 1.
Derivative of logarithm is basically if y is equal to log of x, then the derivative of the logarithm would be 1 over y dy dx. So you basically get this to be d dx of the logarithm. That's just a property of calculus. So that would be, I guess I've written this wrong. This would be log of y. If this was log of y, then the derivative would be 1 over y dy dx. That's the better way to write it. So, property of logarithms, if you take the derivative, you just get that property. So, this would then be, here's the one, this is, the y is like the k. There's the x. You get minus kT over Q, and this would now be d dx of logarithm of k. Okay, we're getting there. Now, what we really want is we want to evaluate this across the membrane. We don't really care what's happening within the membrane. We want to find out a relationship between the voltage difference across the membrane and the concentration gradient across the membrane. So let's integrate this differential equation across the cell membrane. So we'll get integral from, and I'll just write from out to in of the v dx, now integrate it over x. So that's that, equals minus k t over q integral out to n of d dx log of k dx. All right, so what is the integral of dv dx times dx? V, it's the fundamental theorem of calculus. If you take the integral of a derivative, those two things just cancel out. It's actually the integral of the V inside minus the V outside. We're going to assume that the voltage outside is grounded. So V out is equal to 0. So you get 1 minus 0, basically. So this is just equal to inside voltage. So we have an expression for the inside voltage. It has a minus k t over q. And now here is, again, the integral of a derivative. That's one of the reasons why we use this trick. We have it as a total derivative. So those cancel, and you just get logarithm of the concentration. So we'll get log of k, and that's on the inside, minus log of k on the outside. Out. And big bracket. Alright, so I'm running out of room. So I'm going to have to erase some of this. Any questions about this part before I erase this? Okay. So, we're almost there. What we have now is V inside, so that's really the voltage across the membrane because the outside's grounded, is equal to, well, this is going to be log of Kn over K out. The difference of the two logs is the log of the ratio. And I'm going to put the K out on top and the Kn on the bottom, which means we get rid of the minus sign. Because if I extended this minus sign in here, it'd be K out minus Kn. So you're going to get Vn is K T over Q log of K out over K in. And that is exactly the Nernst equation that we saw previously. If you derived it for the concentration outside, you would get QV over KT, and then as an exponential of that, if you derived it for Kn, you'd end up getting a minus the exponential of QV over KT, which is exactly the Boltzmann factor. So it's the same physics we saw before. We have a different view of it. So what's this say? This says that here's your membrane. Here's your potassium channel. And there's a lot of potassium on the inside, just a little bit on the outside. So what's going to happen? It's going to start diffusing out. It's going to diffuse down this concentration gradient. But it's a charged molecule. So it brings its positive charge out here. And as it brings positive charge piles up on the membrane, leaving negative chlorine ions, which couldn't go through with it, on the inside of the membrane. And so you develop this electric field that's pointing down in the membrane. You have a voltage, a negative voltage inside compared to the outside. So this electric field, which is also present in here, eventually starts pushing the potassium out. And eventually it reaches the equilibrium, the fusion pushing it out, I guess, and electric field pushing it in. And you have the equilibrium given by the Nernst potential. So that's what happens with if you have a purely potassium ion channel that's open at rest, which is essentially what happens with the resting potential. Now, you can calculate Kt over Q. Q is just the charge of one ion, positive ion. Kt, this is Boltzmann's constant times body temperature. And you have to know what the concentration gradient is. But the concentration gradient, there's a lot more inside than outside. So this ratio is less than 1. The logarithm of a number less than 1 is negative. So you end up finding that the resting potential, Vm, the voltage across the membrane, is approximately, if you put in reasonable numbers, minus 70 millivolts resting potential. So cells typically have somewhere on the order of minus 70 millivolts across their membrane at rest. Okay, so that's a little bit about how they maintain their resting potential. And slowly, the potassium would end up eventually leaking out if you gave it a lot of time. This is not truly going to be a steady state situation. You could slowly lose potassium, and this would drain down, except that the pump will continue to pump the potassium back in order to maintain the stable resting potential. All right. Next topic I want to talk about is the membrane capacitance. So let us talk a little bit about membrane capacitance. All right. Now, yes?
To calculate the voltage across the membrane, did you use the Nernst equation?
I use the Nernst equation, yes, which we derived down 2 different ways. I didn't tell you exactly what concentrations I used, but typically inside the cell is like 150 millimolar potassium, and the outside is maybe 5 millimolar. That's roughly the concentration gradient. I use body temperature. I use a charge of 1.6 times 10 to the minus 19, which is the charge of a single ion. Okay, so we found that we get charge building up across this membrane. The membrane acts like a capacitor. Remember, a capacitor is like 2 plates, which you have positive charge on one, negative charge on the other, and you can store that charge. So a capacitor has a certain capacitance. So there's a relationship between the charge on the capacitor and the voltage across the capacitor and the capacitance. It's Q equals CV, where C is the capacitance and V is the voltage and Q is the charge. Okay, so we have to know what units these are in. First of all, what is the units for capacitance? Anybody know that? Farads. Capacitance is in a farad, which is short for Faraday, who worked on some of the early work. And a farad, it can be thought of as just the unit of a coulomb per volt. So now this is confusing because here I'm using C for coulomb. Coulomb is the unit of charge. And here I'm using C for capacitance. Now, if this was typed in a book, usually the symbols for variables are italicized and the units are not. So it wouldn't be quite so confusing. But when I write on the board, you have to realize that capacitance, whether it's a symbol or a unit. Okay, so it gets a little bit confusing. Here's another one that gets confusing. The units for voltage is volts, which is just V. So you can get really weird looking equations like V is equal to 15 volts Looks like the V's ought to cancel, but no, that's a symbol and that's a unit. Okay, so you just have to get used to these various units and what's happening. All right, so Coulomb is the volt to be farad is usually F. Now, does anybody remember what the equation is for the capacitance for a parallel plate capacitor from your basic physics class? Here's a capacitor, and it has a plate area A and a separation D between the plates. So the capacitance, well, how's it going to depend on A? Is it going to get bigger or smaller?
Bigger.
Bigger. You make A bigger, you make the capacitance bigger. So you're going to get A. How about D? If you make them closer together, smaller, does that increase or decrease the capacitance? Increase. So you get an A over D. And then the other thing that comes in is it depends on what material is in here. But if you have a material, you have a dielectric constant kappa. And then there's this epsilon naught, which is a constant from electricity. So kappa is the dielectric constant, which is a dimensionless number. All right. Now, suppose we want to calculate the membrane capacitance per unit area, often given C sub m. This is going to be something that we'll be using a lot in bioelectricity. If it's capacitance per unit area, so its units are farads per meter squared, well, that would just bring the A over here. You get kappa epsilon naught over D. Okay, so all lipids have sort of roughly the same dielectric constant. It's approximately 7. Epsilon naught is just a constant from electricity. It's 8.85 times 10 to the minus 12 farads per meter. You can write epsilon naught as number of farads per meter. And D is that thickness, which we said was about 6 nanometers. 6 times 10 to the minus 9 meters. Okay, well, the 6 and the 7 can almost cancel, so it's like a little bit bigger than 1. This is, so roughly that times 8 is about 10 times 10 to the minus 3. So you're going to get approximately 10 to the minus 2, or 0.01 farads per meter squared as your capacitance. Now, oftentimes in older literature, you'll see this written with different units. You'll see this written as in microfarads, which is, there's 10 to the 6. Let me write it this way. 10 to the 6 microfarads per farad. And you'll see the same distances written in centimeters instead of meters. So there is 100 centimeters per meter, but this is all squared. So this is actually 10 to the 4th down here. 10 to the 6 over 100 squared, or 10 to the 4th, is 100 times 0.01. This becomes 1 microfarad per centimeter squared for the membrane capacitance. A nice, easy number to remember in these units. So now, when you're dealing with biology, you don't usually have very many constants like you do in physics. Physics has the gravitational constant, has epsilon naught, it has mu naught in magnetism, speed of light. But in biology, it doesn't have a lot of constants, but this is pretty much a biological constant. Most membranes very rarely vary in their thickness, and they don't vary that much. They're bilipid layers. They don't vary that much in their dielectric constant. So all membranes have roughly a capacitance per unit area of 1 microfarad per centimeter squared. It's kind of a handy thing to remember. So it's close to a biological constant as you're going to get. So let us now move on and look at one of the problems from the book. Any questions on that first? Okay. Alrighty, so I want to do now problem 6.18. It's not in your homework, but it's an important problem. And let me tell you why we're doing this problem before we do it. We want to answer one fundamental question. That is, when charge comes into a cell and changes the voltage, say during an action potential, charge will come in, usually it's sodium, and might change the voltage by, say, 100 millivolts. Does enough charge move in, enough sodium move into the cell to significantly change the concentration of sodium? Or is it just a very small number compared to the amount of sodium that's already in the cell and the amount of potassium? So that's what we want to look at. We want to look at basically how much, let's consider the case of potassium. The potassium was going to diffuse out and spread in the membrane. Did that significantly change the potassium concentration? So that's what we're ultimately trying to answer in problem 6.18. So it says, for an unmyelinated axon of table 6.1 and figure 6.3, so we'll talk later about what myelination and unmyelinated means. How many sodium, potassium, and miscellaneous anions are in a 1 millimeter segment? Okay, so we're going to have a piece of nerve axon. Now, an axon is, we have a nerve cell, and axons are the cylindrical things that stick out from the nerve, and that's what carries the electrical signal. So the axon can be very long and thin. So for instance, an axon from your head down to your hand might be, a single axon might be nearly a meter long. So these are long axons. We're looking at a 1 millimeter segment. So I'll call that delta x equals 1 millimeter. And if you look in the table, a typical axon in your body is 5 microns in radius. Okay? They vary, and the speeds of propagation down the axons vary, but that's typical. And ion concentrations, well, there's a lot of sodium outside. So inside, it's not very high, 15 millimolar. But outside, it's more like 150 millimolar. Remember when we made isotonic saline? Saline with the same osmotic pressure as our blood. We ended up taking 150 millimolar of sodium, 150 millimolar of chlorine, put them together, we got 300 milliosmol concentration. So it makes a lot of sense that this is about 150 millimolar. And potassium is also going to be a lot of it inside, so we'll take that as, okay, now if I'm following my notes rigorously, which I should do, this was 145 instead of 150. And the potassium inside is 150. And the potassium outside is 5. So there's hardly any potassium outside, hardly any sodium inside. That's that pump that maintains that. Okay, so we want to figure out how many sodium ions are in this 1 millimeter segment. How are we going to do that? How can you figure out how many sodium ions are in there? What do we need? Pardon?
Volume.
Volume. We have a concentration. If we just multiply it by the volume, we get the total number of sodium ions in. So the sodium ion concentration inside is 15 millimolar. So 15 times 10 to the minus 3 molar, which is going to be moles per liter, times the volume. We need to calculate the volume of this thing. Well, the volume is going to be distance, delta x, times cross-sectional area, pi r squared. That's r, the radius. That's going to be the volume of this. So 1 millimeter is 10 to the minus 3 meters. Pi R is 5 microns. So we square that, we get 25 times, that's 10 to the minus 6, but when you square it, you get 10 to the minus 12 meters squared. So that's going to be pi times 25, that's somewhere around 80. It's going to be about, and this is, let's see, the calculator's not, yeah, it's about 79 times 10 to the minus 3, 12, that's 10 to the minus 15 meters cubed, which is 79 times 10 to the minus 12 liters is the volume if we want it in liters. Okay. 79 times 10 to the minus 12 liters. Liters cancel. You get 15 times 79. That's going to be 100 and... Let's see, what are we doing? We're doing... I'm doing sodium. Sodium comes out to be about 120 times 10 to the minus 15. It comes out to be, let me do the calculation. Where's my calculator? I know I brought it. Maybe I didn't. Okay, I'll just use what I have in my notes here. I got 100. Oh, I see. Yes, I'm in good shape. I need to multiply its moles, and they wanted to know the number of molecules. So I got to convert from Avogadro's number. 6 times 10 to the 23 molecules, or ions, I should write in this case, per mole. And so I get 23 minus 15. That's going to be about times 10 to the 8th, but that's 6 times 120. You end up getting approximately 0.72 times 10 to the 12th ions inside. That's the number of sodium ions. So that would be Na inside. Potassium ions inside? Well, the potassium ion concentration is just 10 times larger. Volume's the same, so you get 7.2 times 10 to the 12th ions inside. This is not actually the concentration. This would be the number of sodiums. Number of sodium ions. This would be number of potassium ions in that 1 millimeter segment. All right, so we did that. Then the next part asks how many water molecules. Just wants you to compare. Basically, what we're trying to figure out is whether there's a relative concentration of water and ions. You expect this to be fairly high concentration of water, but we can do this. We can get the concentration of water, which you've calculated in a homework assignment before, and I think you calculated it again, maybe in another assignment. 55 moles per liter is the concentration of water times the same volume. It's going to give you, in the end, 2600 times 10 to the 12th number water molecules. Writing everything times 10 to the 12th so you can compare. There's a lot of water molecules for every ion. What that means is that it's a fairly low concentration in the sense that mostly it's all water with just occasionally an ion popping up here and there. So it's one potassium ion, which is the most prevalent one, for every 320 sodium or water molecules. So not too many. Okay, through C. What's the charge per unit area on the inside of the membrane? Charge per unit area. How would we find charge per unit area? How do you find charge on the membrane? Think of it as a capacitor. Well, you you take the capacitance times the voltage, and that's going to equal the charge. And if you want the charge per unit area, you can take the capacitance per unit area times the voltage. So, we calculated the capacitance per unit area. So this is going to be charge per unit area, which is going to be 0.01 farads per meter squared. In other words, 1 microfarad per centimeter squared. That's the capacitance per unit area times the voltage, which we said was about 0.07 volts, 70 millivolts. If you calculate this out, you get 0.0007, and again, coulombs per meter squared. That is the unit, coulomb per meter squared. Now, that's the charge per unit area. What's the fraction of all the atoms and ions inside the segment that are on the membrane contributing to this charge? So what we really need to do is, first of all, we need to figure out what the total charge on the membrane is. So we multiply by the area. And then we're going to use Avogadro's number to relate the charge, and we're going to use the charge of a single ion. It's really the charge of a single ion to get the total number of ions are on there. So we need, first of all, the area. What's the area of this membrane? 2 pi r times delta x. The length times the circumference, which is going to be 2 pi 5 times 10 to the minus 6 times 10 to the minus 3. Which, did I go through and calculate this out? Yes, I did. Oh, that's 2 times pi. That's roughly 6 times 5. So that's something on the order of 30. It's actually 31 if you be exact. Times 10 to the minus 6 and 10 to the minus 3 gives you 10 to the minus 9 meters squared. So the amount of charge on this membrane is going to be charge per unit area, which we calculated, times the area. So it's 0.07, there's another 0, coulombs per meter squared, times 31 times 10 to the minus 9 meters squared. So this is like 0.7 times 10 to the minus 3, so you're going to get something 20 times 10 to the minus 12, something like that. It's actually going to give you 22 times 10 to the minus 12 coulombs of charge. But we want to know how many ions that is. So the number of ions is going to be 22 times 10 to the minus 12 coulombs divided by the charge of a single ion. 1.6 times 10 to the minus 19 coulombs. Coulombs cancel. And this comes out to be 138 times 10 to the 6 ions. Okay, that's how many ions it takes to create sort of the resting potential. Now, let's see. This is the number of potassium ions that are in the cell, and this is the number it takes to create the resting potential. It's somewhat better to write this number as 7,200,000 times 10 to the 6 ions. Just so we can compare these numbers, 10 to the 6 we can compare. This is over 7 million, this is 138. So what it says is it only takes a tiny, tiny fraction of the total potassium in the cell in order to create this voltage change, this voltage on the cell membrane. So what are the implications? Implications are that when you're firing action potentials in the nerve, and we'll talk about action potentials in detail in a later class, and you're going to change the voltage across the cell membrane, usually that happens by sodium rushing in and then later potassium rushing out. Almost no change to the action potential, to the voltages, the Nernst potentials, driving these into the concentrations of the ions. It's only if you fired action potentials all day, maybe you can slowly accumulate these changes. This is why if you do an experiment with a nerve, and you take the nerve out of the animal, and you stick it in a dish surrounded by saline, you can do experiments on that nerve all day, and it'll fire action potentials. The pumps, you've removed it from all the metabolism of the body, so the pumps don't work anymore, yet you can sit there and you can do experiments all day. Thousands and thousands of action potentials, until finally so many action potentials that your concentration gradients will eventually decay down. And that's exactly what Hodgkin and Huxley did when they figured out how nerves work, and we'll talk about their model in detail. But I wanted you to realize that unless your cells is really small, you aren't changing the concentrations much when you put these ions on the membrane. If you found a cell that was really tiny, a micron or something in size, you can begin to get to where you have a significant effect on the concentration. But there's also cells bigger than this, so the effect's even smaller. Hodgkin and Huxley used a giant nerve axon of almost a millimeter in diameter. They could work on that for, almost unlimited number of action potentials. They could just work on it all day. And that's what electrophysiologists often do all day. Okay. So let's get to talk a little bit about Hodgkin and Huxley. But first, any questions on this before I start erasing it all? Okay. So now let's begin to talk about how nerves work. Okay, so let's start in 1936 with J.Z. Young, an Englishman. He's the one who discovered the squid nerve axon. So, an ocean animal, you take it out, you capture the squid, dissect it. You can dissect out this nerve, and the nerve's about a millimeter in diameter. So it's huge. You can stick electrodes into the nerve fairly easily and make these electrical measurements. So it's really what allows you to be able to do these experiments. There's a nice YouTube video about Young and his discovery of the squid nerve axon, and I'm going to send you the link. I want you to consider this to be required viewing in the sense that I could ask a question about the video from an exam. So I expect you to look. It's only like 5 minutes long or even less than that. Short little video, but it shows the squid, it shows the dissection, and it shows the nerve and how you can analyze it. I'll send you the link through Moodle. Okay, so now we have this giant nerve axon. In fact, it's kind of funny that when Hodgkin and Huxley, who first discovered how nerves work, got the Nobel Prize, there was one electrophysiologist, who probably wasn't the most tactful guy in the world, who said it really was the squid that should have gotten the Nobel Prize, because none of this could have been done by the squid, but anybody could have made the same discoveries like Hodgkin and Huxley, but only the squid could have led to the prize. So Hodgkin and Huxley are two English scientists, Alan Hodgkin and Andrew Huxley. And they got the Nobel Prize in 1963 for this work. The work was actually done in the late 1940s, most of it, to try to figure out how nerves work. I'm going to send you their 1952 paper, which is probably the paper that's most cited and really led to the Nobel Prize. So you can see it's a long paper, so I don't expect you to read the whole thing, but we're going to be talking about it in detail in class. So I want you to see what sort of a Nobel Prize winning experiment and publication looks at. We're going to talk about their model for the squid nerve axon. So they made a mathematical model that describes it. And today we're just going to, with the time we have left, we're going to just kind of draw a cartoon about it. And then in future classes, we will actually derive mathematical expressions for these. So let's do our cartoon. And our cartoon starts with the membrane. This is the membrane. This is the outside. This is the inside. Remember, inside lots of potassium, outside lots of sodium. And then you have your channel. And channels are selective, so they can pass either sodium or potassium. And this is going to be a potassium channel, a plus channel. So only potassium can go through there, no sodium. And we said channels are gated. This is going to have a gate that can swing open and close. And we're going to give this gate a name and just call it N. Stupid little name, but I'm not sure what it stands for, but they chose N. N is going to turn out to be a mathematical variable that can either be between 0 and 1. 0, it's closed, 1, it's open. But for now, just think of N as the name of the gate that can swing open and close. There's also going to be sodium channels. So down here ways another type of channel. This is going to be a sodium channel. It only passes sodium. And the sodium channel has two gates, so it's more complicated. One gate they call H, and another gate, which I'll show is closed, they call M. So N, H, and M are the gate variables. This is sort of how the membrane looks at rest. Potassium is somewhat open. The sodium, notice in order for sodium to go through the membrane, both these gates are closed, have to be open. M gate at rest is closed, so there's no sodium passing through the membrane at rest. And then finally there's going to be one other called the leak channel. The leak channel is not really so, it's sort of, it's got a real small conductance, so it's just sort of a fudge factor. And it has no gates, so it doesn't open and close. It's just sort of a miscellaneous channel that can leak small amounts of ions in and out. Now, each of these channels has their own Nernst potential. So, the potassium Nernst potential, we already calculated out what that was. It's about minus 70. They used minus 77. All these parameters depend on the particular species and exact concentrations of ions. They used sodium, the Nernst potential for sodium. Remember, there's lots of sodium outside, and it's out over in the Nernst potential, so there's a positive number, so you get a positive logarithm, and in fact the sodium becomes 50, no minus sign, millivolts. So if you somehow just close the potassium channel, the sodium would tend to come in carrying its positive charge and make the inside positive. So it would reverse the membrane potential. That's essentially what happens with the action potential. And then there's this leak, which is sort of a fudge factor, but they gave it minus 54.4 millivolts. And you end up now, to try to make this a little more quantitative, you end up with an electrical circuit representing the cell membrane. And the electrical circuit looks something like this. Here's the outside. Here's the inside. And it's got four different paths. First of all, it has a capacitance. These membranes have capacitance. It has a potassium channel and a sodium channel. So let me draw the sodium first. That's the conductance of the sodium channel. Usually we talk about conductance instead of resistance. They're just reciprocals. Conductance of the sodium channel. And the sodium channel has these gates. So I draw, its conductance varies according to the state of the gates. So this little line with the arrow means it's a variable resistor. Depends on the gates. And it has this Nernst potential, 50 millivolts. So inside is going to be positive. So the battery, the thick negative side, and the long positive side looks like this. That's the E NA, or VNA, I guess I'm calling it. That's the voltage across. It's in series with the channel conductance. And then you have two more, VK, which also has a conductance which varies depending on the gate. Its nurse potential has the opposite sign. So it's got the big side of the battery and the little side of the battery. And then there's the leak. And since the leak doesn't have any gates, we don't have a line through it. It's not a variable resistor. It does have a nurse potential. Looks a lot like potassium. This is VK, V leak. And there is your mathematical, your circuit diagram for the squid nerve axon. Now at rest, this conductance is essentially zero because that M gate's completely closed. So you have this conductance is somewhat open, but there's also this leak. And it turns out that the leak and the potassium nurse potential sort of are both active. So the resting potential turns out between minus 77 and minus 54. And if you work it out, it comes out to be the resting potential is minus 65 millivolts for the squid nerve axon. Oh, it's not too far from the minus 70 that we assumed before. So one more thing, let's see if we can write this as a mathematical equation now. I'll do it right down here. The total current through the membrane is equal to 4 terms. Now, how do you express the current through a capacitor? Anybody remember that? How do you ever get current through a capacitor? Voltage has to be changing. If the voltage is constant, the capacitor just acts like an open circuit. So this is really going to be Cm times dV dt. The voltage across the cell membrane is V. And this is going to be a current per unit area because that's capacitance per unit area. Plus, we have, let's see how I'm going to write it, GNA, which could vary with time because its conductance varies. And you have V minus the voltage of the battery. And you get a plus GK V minus VK plus V leak V minus V leak. And that now is the beginnings of our mathematical model for the current for the squid nerve axon. Notice that the total current is really, for the most part, zero. If there can't be a net current going in or out, if it's because that would essentially be charging up the inside of the cell, unless you happen to have an electrode stimulating the nerve. I is going to be zero, but that will really give you a big differential equation for V. So what this is a giant differential equation for the voltage across the cell membrane. And it's going to depend on how these conductances change, which is what's going to be the main topic in the next class. We'll find that we can relate these conductances to N, H, and M, and we can actually get a system of 4 differential equations that will describe the nerve membrane. But we'll talk about that more on Wednesday. So, I will send you the Hodgkin-Huxley paper. I will send you the link for the Young's video about the squid nerve axon, and we will delve into the Hodgkin-Huxley model more on Wednesday. Okay, if you haven't gotten your homework back and you want it, I have it up here.